All right, getting started a little bit late here. Well, a lot a bit late. It's 9:45. So what I'm noticing is like yesterday and today, I had a hard time getting started, getting on stream. That seems to be like my biggest stumbling block. Like I burned 45 minutes or even more than that this morning, to be honest, because I finished my shower and breakfast early. Instead of getting on stream early, I wasted time on YouTube. So that's the hazard that I'm like need to be conscious of moving forward. Is I need to be, I did do a little bit. What happened is I woke up this morning and I did that little tiny stream where I hopped on for just a little while, and I was like, oh, that gives me an excuse not to get on at 9 this morning. No, that wasn't a good excuse, but somewhere in my brain thought it was a good excuse. Okay. Well, I have MAT this afternoon, so I don't have a lot of time to study today, to be honest. So I shouldn't have been wasting time. What is it that we want to do? Do we want to continue on this cache lab? Do we want to abort the cache lab? I feel like I should do the cache lab. Just like suck it up, Buttercup, and do it. Okay, let's do it. I was like watching the lecture last night about exceptional control flow. There's 2 lectures on that. I watched the first lecture and I rewatched it in the evening after I got off stream. Just kind of like in the background while I was doing like house chores and stuff. And what I kind of started thinking is like, I kind of know all this because I read that the Linux programming interface. Like they cover a lot of this material in that book. Not at the same level of depth though. So I might get something out of reading this material, but I don't think the exceptional control flow chapter I'll get a lot out of doing practice problems and like going super deep on. Just because I already know like at the level that I need to feel confident of my knowledge, I've already kind of like hit that level. Sure, I can't tell you exactly which pin on x86-64 or AMD64 chip gets a signal, brought up to indicate an hardware interrupt, but I don't think it's really necessary for my life to know those details. I really feel like the Linux programming interface was like getting me comfortable with the syscall boundary, like writing programs in C mostly that talk directly to the kernel and instrumenting user space programs to be able to understand what syscalls they make to the kernel and how they make them. So that really was the mission of like consuming the Linux programming interface and doing all the exercises I did in that book. This book has been more, let's get comfortable with the interface of x86-64 assembly, like writing instructions directly or being able to understand the instructions that the compiler outputs, and not really going much further down into the CPU microarchitecture. But of course, the book covers microarchitecture implementations. This cache lab is a good example of that. That is like all of caching is below the ISA boundary. But stuff that you need to be aware of if you intend to write performance critical code. So yeah, I guess from that perspective, I can value this cache lab exercise as being something worthy of spending time on, because I will learn more about, at least in theory, because it's a simulation, in theory how caches operate. Um, Even though I kind of have a good sense for that already, I feel like doing the lab will give me an even better sense of that. So this will be a good experience for me. But looking forward in the material, I don't think I'm going to spend a lot of time doing problems. If I go, I just open up the README here and go up here. So we have ahead of us, we have the exceptional control flow stuff. I don't think I'm going to spend a lot of time doing problems from that. Because like look at it, exception handling, cost exceptions, and Linux AMD x86-64, processes, logical control flow, concurrent flows, private address space, user and kernel modes, context switches. I might get a little bit out of like learning more of this in detail, because the lecture did touch on this. Like the context switch is, I knew it was saving off the register file, like the set of registers, including the instruction pointer. As you know, you have to save that off when you do a context switch. But what I wasn't aware of was the other thing that the CPU has to save off, which is, I forgot last night. I guess that's why I need to read this material again, because it's not on the tip of my brain. So you have your register set that gets saved off. What else is part of the execution context? Let me think. Oh, the virtual memory mapping, because each process has its own virtual memory. So I guess it would be like the some state in the MMU or TLB that gets saved off during the context switch. I will definitely learn more about that when I read the Operating System's 3 Easy Pieces book, because I know they talk a lot about implementation of the TLB in the MMU. And I think the way it works is like each PID, each process ID gets its own kind of like entry in the TLB that kind of signifies like, okay, I have ownership of this mapping, this set of mappings. But I don't know the details of how that's implemented, to be honest. Anyways, so yeah, I will get a lot out of reading this material. I don't know if I really want to go deeper into like spending a huge amount of time with it. System call, error handling, that I could spend 0 time on. Process control, obtaining process IDs, creating and terminating. All this is like reaping, putting process to sleep, loading and running programs, using forecast. See, all of this section, the Linux programming interface, covers all of this stuff. So don't need it. And signals, I mean, the Linux programming interface goes so deep on signals, like I just don't really want to spend more time on signals. So I might just speed read this, because I mean, the way that they present it might be interesting, but like I already know everything I need to know about signals. Non-local jumps as well. The Linux programming interface covers that. Tools terminating, I'm sure that's small, but you know, I'll read it. So I'll read all this, but I think I need to speed read this stuff here. And then virtual memory is the chapter that I want to spend more time on. And then I'm just going to skip these, and I might even skip concurrent programming, to be honest. And just watch the lectures, because I get a lot of the, yeah, I'm going to go ahead and say skip this, because I already know most of this. So virtual memory really will be the last thing that I spend a lot of time on reading, at least, and doing problem sets on. And then the rest I'm just going to cover through lecture and through labs, and if there's an exam posted on the website somewhere, maybe I'll take the exam and see how well I do. This I can, since I'm skipping this stuff, I'm just going to put tildes around this. No. TLPI covered. Oh, come on. What are you doing? Oops. So maybe I can do a GW here on these and then space this in like that. Yeah. GW. Yeah. There we go. So why did this not strike that out? Curious why that failed. Well, let's go ahead and grip on that. See where we're at. Okay. Oh, that's right. I was working on this. I'll come back to this later. Let's send this to a different terminal. So you're gonna actually, that is in the right terminal, right? Yeah. Let's go back over here. Kill grip. Foreground this. We're gonna go down to oops, here where we skip these, and we'll put reasons here. So this is the same reason why I skipped this whole chapter. I'll just say I don't want to be insulting. Not relevant to my learning objectives. And then we go down here. Okay. Why didn't I do the practice problems on the SIMD? Oh, is that? Yeah, I didn't like that handout. It wasn't a good introduction to SIMD. Okay. Yeah, they got a buffer lab. Is that even here? No, we have attack bomb cache data, malloc proxy shell. There's not even any performance. Cache. There's 1, 2, 3, 4, 5, 6, 7. Yeah, those are the 7 here. This thing, the colors are all whack, man. Like, look how messed up these colors are. And the markdown stuff. Alright, I think that covers all the changes I wanted to make to the README. Can I do like an X here or something to like gray it out? What are the states of GitHub markdown checklist boxes, and how do you represent them in text? Okay, so there's no intermediate form. And we can verify that by putting a dash here. And that should grip. Oops, a grip. That should show up here now. That was like a messed up one. Okay. Okay, let's kill this. You're gone. We'll go back here. Get status, get add all, get DC, review, just some markdown fixes. We gotta fix that. Oops, please go away. Vim readme, we gotta fix chapter 10 at the end there. Okay. 12. Okay, alright, let's go ahead and resume reading this handout. Part A, we will write a cache simulator in csim.c that takes a Valgrind memory trace as input, simulates the hit-miss behavior of a cache memory on this trace, and outputs the total number of hits, misses, and evictions. We have provided you with a binary executable for a reference cache simulator called csimref that simulates the behavior of a cache with arbitrary size and associativity on a Valgrind trace file. It uses the LOU least recently used replacement policy when choosing which cache line to evict. The reference simulator takes the following command line arguments. So you can say csimref number set index bits. This is going to be, we'll say 4. Associativity, number of lines per bit. We'll say what? We'll do 32. And then block bits are going to be, well, if you have 32, 2, 4, 8, 16, 32. That'd be 5 bits. And set will be 4 bits. It's 9 bits. And then subtracts 9 from 64 bits of the address. Well, we'll just do 4 here. We don't have to do it crazy. And then trace file, name of Valgrind, trace to replay, traces. And we'll just do like a long trace here. Sorry, /. Hits, misses, evictions, okay. Your job for part A is to fill in csim.c file so that it takes the same command line arguments and produces the identical output as reference simulator. Notice that this file is almost completely empty. You'll need to write it from scratch. Program, so csim.c. So the first thing is to arg parse, and then we need to create a cache simulation, which will be, why is this all fucked up here? Create a cache simulation which will contain the cache data structures. So stupid. And then we'll also, okay, for some reason it wants 2 spaces there. Also fetching new memory logic around reads and writes to main memory. Data bits are not important, just hits, misses. Calculation. So that seems pretty easy to implement. So let's start with the arg parse. So we got a bunch of shit here. So you have dash, just gonna list everything, -h, -v, -s, -e, -b, -t. If I leave one of these off in the simulator, like say I do like something like this, it's gonna like say, hey, you need to specify everything. So S, E, B. Usually if it's a requirement, I don't actually do flags for that. Just pass them in as arguments, like the file here. Like all these things are required, then just do them as positional arguments. But I guess they wanted to do something like allow you to do something where you reorder them. Yeah. Okay. This will be fun. And then H and V. What is optional verbose? What does verbose do? It just prints out the trace itself. If I do a head on a trace long here, traces/long trace, you can kind of see. Let's do tail here, or we'll do less and go down the bottom. So you can have a double hit. Okay. Okay. And then the last part is actually to run the simulation. So this will involve reading trace data from from file, parsing it, and taking actions on the state of the simulation. And then finally, the last bit will be output state of simulation. Which is basically this thing here. Okay, they want us to use arg parse, I think, right? before we jump into that, let's finish reading this section. Your job, programming rules for part A include your name and login ID. I don't give a shit about that. Your csim.c file must compile without warnings in order to receive credit. Do we have a make file for this? I think there's like a make file. Yeah. So that's this guy here. Oops. CacheLab.c already has stuff. Why do we need this? This is the transpose matrix stuff and a print summary function. So this is for the second part of the lab. All that, the transpose function. Okay. Cool. Let's undo that because I just want to. Well, can't write it then, can I? So that's that. Test trans and trace gen. Don't want to get into that yet. What is trace gen? That also involves trans. Okay, so that's all trans stuff. Transpose. We'll just get status, get diff. What's under this dot? Vim.csim results. I don't know where that came from. Rip grep for csim results. So that's where that'd be CacheLab C and test trans. CacheLab C. So that's the print summary here. So not only is it printed out, but they open a file, they assert that the file is there, then it writes it to the file as well, and then closes it, and they open it in what mode? Just write mode. So I think that will overwrite. But I don't want to commit that, so I'm going to say get ignore. You're going to get a .csim results. Add it to you. Get add, get ignore. Oops. Do that. Get status. Get checkout cache lab.c. Get status. There we go. Jobs. Foreground. Quit that. And then get div. This is just my comments. Okay. Okay. So I'm just learning the repo here. Include your name and login ID in the header. Comment for csim. Compile without warnings. Your simulator must work correctly for arbitrary S, E, and B. This means that you will need to allocate storage for your simulator's data structures using malloc function. Don't need to have help with that. For this lab, we are interested only in data cache performance. So your simulator should ignore all instruction cache access. Line starting with I. Okay. I lines can be ignored. Recall that Valgrind always puts I in the first column with no preceding space, and M, L, and S in the second column with a preceding space. This may help you parse the trace. To receive credit for part A, you must call the function print summary with a total number of hits, misses, and evictions at the end of your main function. Print summary, so and so. For this lab, you should assume that memory accesses are aligned properly. Such that a single memory access never crosses block boundaries. By making this assumption, you can ignore the request sizes in the Valgrind traces. Yeah, okay. Okay. So then there's part B. I don't give a shit about that, but this is how they're going to evaluate. So for part A, we will run your cache simulator using different cache parameters and traces. There are 8 test cases, each worth 3 points, except for the last case, which was worth 6 points. So you run that. Where's this 1, 4? Oh, here. Then you can use the reference simulator csymref to obtain the correct answer for each of these test cases. During debugging, use -v option for a detailed record of each hit and miss. For each test case, output the correct number of cache hits. Outputting the correct number of cache hits, misses, and evictions will give you full credit for that case. Each of your reported number of hits, misses, and evictions worth 1/3 of the credit for that test case. That is, if a particular test case is worth 3 points, your simulator output a correct number of hits and misses, but reports the wrong number of evictions, you'll earn 2 points. And then this is evaluation for part B, which we're going to skip right now. Working on the lab. Working on part A, we have provided you with an auto grading program called Test CSIM that tests the correctness of your cache simulator on reference traces. Be sure to compile your simulator before you run the tests. Okay. For each test, it shows the number of points you earn, cache parameters, input trace file, and a comparison of the results from your simulator and a reference. Here are some hints and suggestions for working on part A. Put your initial debugging on the small traces such as traces.dave.trace. The reference simulator takes an optional -v argument that enables verbose output. Displaying the hits, misses, evictions that occur on the result of each memory access. You're not required to implement this feature in your CSIM C code, but we strongly recommend that you do so. It will help you debug and allow you to directly compare the behavior of your simulator with the reference simulator on the reference trace files. We recommend that you use getopt function to parse your command line arguments. You'll need the following header files. All right. Getopt.h stdlib.h, and then unistandard man2 or man3 getopt. There should be some like code here already, right? Some example code, yeah, this thing here. Opt is an int. We need to give it argc and argv. It's a pointer to char star. How do they do the main in C? There you go. Yeah, I thought it was a char star array. Alright, so here, let's go up here, get our function parse command line arguments. We give it argc and argv, and we give it the op string. So I'm interested in the specification of op string. Search for that. Combination of legitimate option characters. don't really give a shit about how this fucking thing works. SEBT. And we'll say int opt. Switch on opt case is going to be S E. What are these flags again? S is jump over till cache. CSIM ref H. So S num. Where's opt arg? S E B This will be block bits. This will be lines per set. This will be set bits. And that's good for that. Obviously this needs to be updated here with the same usage here. Oops. Okay. Just print out the state of these variables now. %d, new line, x, let's say something like x. So this is going to be set bits. I need to clear these set bits. Oops. This will be int set. Actually, I don't need to initialize these. They have to be set. So we do block bits, lines per set, and finally a char star for file name. Block bits. Okay. Okay, we need to have printf now. Fix that. Okay, looks reasonably well for argument parsing. Make csim. Let's go ahead and make sure these don't get committed here. What's this C0 handin.tar? hand in. Just tars everything up. Don't need this. Test trans, trace gen, trans O. Okay. Interesting that it was 0 initialized. So E. Okay. If we vim up csim.c, where does this opt-arg thing come from? Is it global that gets set by get opt? It's like so sloppy. I hate all this C shit that uses globals everywhere. It's just a lot of like magic. It's side effects. Like you could call get on and give it the argc and the argv and your option string, and then you could give it the things that you want it to write to, or even the one place that you want the char star to land, and then return opt. Like one more argument here would make it to where you don't need opt arg, and it's not you can call it concurrently, you can call it in I mean, I guess it's not really needed to be called concurrently, but it's just generally good practice to, like, if you wanted to say like write tests against get-opt, then you have to now monkey patch all these freaking globals, and it's sloppy. I don't mind passing in pointers to things that I wanted to, where I wanted to write results to, but I think that's a reasonable API because it allows the caller to perform its own allocation strategy instead of assuming an allocation strategy for the caller using like make, and then also having to like have the caller free things afterwards. Which is fine. That's another fine API. Like, but it just it imposes a allocation strategy on the caller and requires the caller to like participate in the memory management of that allocation strategy. Whereas if you just say, hey, give me the place in memory that you want me to write this shit, and then the caller has to kind of orchestrate that. So yeah, I'm not a fan of the opt-arg thing. And I don't know why it's segmentation faulted on me. Let's see if we can debug that. Like what would cause that? A break of the switch. Yeah, let's try just using GDB. Vim up the make file and make sure that we're building with -g. Yeah. And I want -og as well, just in case. Make. Oh, here we go. File name. Yeah, I mean, they are uninitialized. Say -1 here. -1. Now we can test it against like an error state. And is equal to null. Oops. There we go. Make clean. Make csim-e gdb bang bang. Breakpoint on csim.c line 24. Restart. Yes. Just layout ASM. C. Help TUI layout. TUI layout. Split. Layout splits. No source available. Layout ASM then. And if I actually layout none. Actually, let me just do this. Breakpoint on csim.c 24. Restart, yes. Finish. Main. So we want to set a breakpoint. We got our get opt call. So the switch is going to be one of these things. I don't see the get up call though. Do you? Call stir too long at PLT. Here's the get up call. It jumps to CF. Which is, where's CF? Get up jumps to CF, 2CF. 2CF is down here. So that's if it's a negative. That's the error handling. So we're not going to hit error handling. Well, we'll just step through it. I'll just set a breakpoint on the getUp call. So we get 69. Print as a char. E. So this is our E. So we handled a negative. Now we're compared to 73. And if we look at Python, char of 73 is going to be I. So we don't do that one. Okay, so we hit that case, which was before here. We are at 26D. So if we look at 26D, we're comparing to 45. 45 should be our E. 45 is our dash. Ooh, interesting. Can I, in this context, print a char star of a symbol, a local symbol, or I guess it's global, which is going to be our opt_arg. No. Print out opt. Well, it would have been an EAX. It is 69. E. Hex 69 would show up as 45. Okay, that's why it's there. Okay. Okay. Let's see where we segmentation fault. So we move A into EDX. So we're trying to do our stir to L. So right at our call, so we moved A into EDX, 0 into ESI, and this other location off of our instruction pointer into RDI. And this is telling me that it's the opt_arg symbol. So let's go ahead and print that out. Print out char star of opt_arg. It still says that. So let's go ahead and get the address, which is an RDI now, I believe. Yeah. So print out or extract I think I have to say print char star right here. Char star RDI. But I have to extract it. Can I say extract char star like that? Extract string. Can I do that? At RDI. Let's just print out $RDI. How is that 0? Oh, because I didn't give it an argument. So you have to make sure that there is a value there. Because this GDB... No, I gave it a value. I gave it EASDF. csim-EASDF. Still core dumps. So let's go ahead and run this again. That wasn't what I thought it was. Disassemble. Sorry, breakpoint main. Restart. Yes, disassemble. And we were down here. Where were we at? We're right before the call here. So put a breakpoint there. Oops. Fix this. Go. Disassemble. So we're gonna say next, and that's where we get our 6sec-v. So restart, yes, continue, and now we're here. Disassemble. Okay, so print out RDI. Why is that 0? Print out EDX. Print out ESI. So EDX and ESI, those are just call save registers. Because I'm not passing those arguments. RDI is definitely getting passed in there. But RDI is null. Why is opt-arg null? Let's go ahead and hit up man3, get opt-arg. I don't like this fucking opt-arg thing. Extern charstar opt-arg. I think that means that I need to have like a colons here to get opt-arg set. Maybe that's what it is. Let's do a make, and we'll just run csim-e. Okay, that fixed it. Why is that now a 0? Set bits 2. So we need to check the, if I do a man on 3A2I, return value for 0 on there. What if it's 0 though? Converts the initial portion of the string pointed to by nptr to int. The behavior is the same as stir to L. I like A2AI because that's the Go's version. Stir to L. Except that A2I does not detect errors. Okay, I actually do want to detect errors. The A2L and A toll functions behave the same as A2I, except that they convert the initial portion of the string to the return type of long. So let's do stir to I maybe. Man3 stir to I. Return value, stir to I function always. So it takes in the char star, the end pointer I don't really care about. So maybe we'll change this to be a stir to I. And we give it the opt arg, we give it a null pointer here. Base is 10. The rest of that I don't really care about. Do I have to give it all? Always returns the closest value in the range specified by low and high arguments. The error no value is guaranteed to be left unchanged. Errors are stored as the conversion status of the R. What the fuck? Is this easier? Start toll. Start to function returns the results of the conversion unless the value would underflow or overflow. If an overflow occurs, stir2l returns long min. If an overflow occurs, stir2l log max. In both cases, error no is set to E range. Precisely the same holds true for stir toll L. 2 L's. What's the difference? Give it the same signature. A long? Yeah, okay. So maybe say stir to L. Make these longs. We need to do some processing here though, where we say error no is equal to 0. And then I think I need to just import that as error no. And then if error no is not equal to yeah. Where does it say error no? This function does not modify error no on success. The given base contains an unsupported value. E range is out of range. Implementation may also set error no to invalid in case the conversion was performed, no digit seen, and 0 returned. So I'm gonna say, hey, if you're not equal to 0, then there's an error here. So we can just say go up here, create a function, void print exit usage, and it basically just does these 2 lines here with arg, well, command, which is a char star, and then this will be command. Okay. And down here we'll say exit usage, and we give it the argv sub 0. Then we go up here, just all one line. If error no is not equal to 0, we exit usage. So we need to do this little dance for each. Set bits. Can we just do like parse? Yeah, let's do that. Make it a little bit simpler here. We'll have like a let's call it a long. Call it parse. Say too long. Too long or exit. And usage. We also want to save it off. So error no, I think we can use it as an int, right? Int is equal to error no temp error no, and then we have error no is equal to 0. Call our thing. Otherwise, we set error no back to temp error no, and we return our value. Calls value. Val is equal to 0, and we call it a long val. I think that'll work. We need a char star command here, and we'll just pass that in here. So too long or exit usage. Do that here. Too long or exit usage set bits is equal to that arg v sub 0. And we'll call this optarg. Optarg too long or exit usage. Then we delete all this. Boop, boop, boop. Delete all this. Lines per set. And block bits. There you go. We can't do that. We have to copy it because optarg is going to change as it's being processed. So we need to say stir len of if optarg is equal to null, then we're going to exit usage, and then we call sternum len on optarg, and then up here we can just pull this out and we can say oops, a char star optarg to string, optarg to stir or exit usage, char star command. Here we go. We say, hey, if you're null, we're going to exit usage, and otherwise we compute your length as an integer or size t, and string.h. This will now be command. Okay, so now we got our len, stir len of optarg. We need a malloc our length plus 1. And we'll call this a char star file or stir. It's equal to that. And then here return stir. And we need to do our stir and copy. Stir and copy. Sorry. And then this is going to be destination, which will be stir. And the source will be optarg, and the length will be our len. And then the last character of our stir, which will be len of stir, sorry, just len. It's equal to the null bytes. Alright. So first we just check for a null string. So we need to have some data there. And then we compute the length. And then we just say if in here len is greater than 255, then we just exit usage. And then we malloc up. We need to test the malloc. Say if stir is equal to null. We're not going to exit usage on this. Printf file name or optarg stir to large. We just do a puts on that. This says, yeah, just exit usage should fix that. We're gonna need to put some braces here now. And then here, we're gonna put yeah. And we'll do it like that. Boom. Puts enable to malloc opt arg stir. Oh, and we need to have the proper equals there. Okay, so now we got our stir, then we copy from source to destination of length, and then we put our last byte there and print out stir, or return stir. And we'll say stir doesn't need to be freed. I need to do a long D here now. And then this will now be opt arg to stir or exit usage. And we give it argv of 0. Okay. Let's go ahead and make sure we got that going. And C stir. Wait a minute. Sorry. CSIM. Okay. We'll do some validation afterwards. But if we do dash T, I think it is, for the file name, ASDF, that gets populated. If we don't do it, okay. If we do E123, that comes through. But if we do ASDF, it should have caught that. I guess it ASDF. How does it not detect that as an invalid error? So if I go back up here and I'll look at my little long parsing here, I'm just going to printf out, and we'll say, hey, parsing stir %s, new line, and give it the opt arg here. Let's go ahead and rerun it. So how does that going into stir2l not produce a error no? What is this value here? It's 20 fucking 2. How is it not that? Make, sorry, man 3 stir to L. If base is 0 or 16, the string may then include 2. Okay. In bases above 10, the letter A okay. Okay, well I can't detect that error, it appears. In Go, it just returns an error. You can inspect it. I hate how complicated this stuff is and how it doesn't do the things that you would expect it to, because you'd expect it to be an error invalid. But does not do that. Okay, let's add some validation on this. So if lines per set is less than 1, then we got problems. Printf, we'll just say hey. Puts. They use fprintf, right? For this thing. Might be a better way of doing it. So in here we say lines, dash E needs to be greater than 0, greater than 0. So you can set this to like negative values here. Let's pull this one up here. Set bits, lines per set, block bits. Then the last one, we'll do T. Can I run this with a empty file name? Yeah. And then we'll say print usage, exit usage, argv sub 0. Oh, and I need to have new lines now because the puts the new lines there. That's going to apply to a lot of stuff here. So fprintf. Can I say args here? Just pull this out as a constant. Okay. And I'll put this in a little scope just to make sure it doesn't pollute my beautiful variables here. Okay. Yeah, I need to scan for fprintf again. Fprintf, and this needs to have a new line now. Scan to it. This one, and those all have it. Okay. Okay. What is this special A there? Never seen that before in A. Okay, step 1 complete. Can't believe it took me that long to get all that done, but it did. This is why we use LMs. Okay, so now we want to create a cache simulation. So let's start with the data structures. I'm going to pull this out here, pull this up. I don't think I need this right now, or this. So I'll go ahead and do it like this. And we'll just write everything out. Okay. So what do we want our data structure to look like? Let's say foo, struct foo. I think that's how you do it, right? Foo. And then you say, if you want to give it a special name, type def that as a foo t. And then in here, so we're going to have our line first. Our line t will have a valid bit. It'll have, and this can be a bool, because we have a standard bool, right? Sorry, boolean. Oh, right and go, bool, like that. Do I need this to get that? Yeah. Okay. So that gives us our valid bit. I'm gonna put that at the end so that it packs well. So we have valid, we have our tag, which, and then some block. We'll just say block could be how many bytes. Char array of 64 would be our proper syntax would be like this. Note not needed for simulation. And then the tag is going to be some number of bits. Some number of bits that will be less than 64. So we'll just make this a u int 64t, and we'll have to include standard int, and yeah, that'll work. What is a bool defined as? It's a bool. Bool is a bool. Can I do like a thing up here where I just say printf out Size of bool. Oops. Is equal to percent D, new line, exit 1. Size of bool. Just 1 byte. Okay. Where's character 80? I want to get up to 80. Something like that, right? Yeah. Okay, so we have our struct line, and then we'll have some type of array for the sets. And we can index into that array, but it has to be variable size. An array yeah. I think the way I want to structure this is that it's going to be a line array. This will be our set. So we can just type def a set as a line array. So I have to do line array as a set t, I should say, and our cache t will be an array of lines or set t's. Why is it complaining there? Expected colon after top level declarator. If I do make here, does it tell me? We'll just make it a pointer then. I mean, that's kind of what I was getting at. A line star. Oh, line T. Yeah, so it's a pointer to a set T is a pointer to a line T. Then a set is an array of lines, and a cache is an array of sets. Okay, so I think that's the data structures that I want. Data. So logic around reads and writes to main memory. We need a hit tracker. So here we're going to have a simulation. So a type def. We could say a struct sim. And we'll call it a sim t. And then here it's going to have its cache t. And it's going to have a hit counter. And this is going to be a uint 64t. Hits. Misses. And what was the last thing? Hits, misses, evictions. And then down here we could say a new sim. And new sim's gonna say new sim down here. It's gonna take in our set bits, lines per set, and block bits. And this is gonna be a sim t s. And those three are all, they all have to be 0 or positive, but they have negative for their validation. Okay, so this is going to be a sim t pointer, I believe. Yeah, will be new sim t taking in these parameters. These are all parameters for the cache size. And they're all going to be a long. And then we're going to have a free t, which is a void free sim, takes in our sim t pointer s and frees it. Okay, I need to take a quick bio break, and I'll be back to work more on the simulation. All right. So what do we want to do with the simulation thing? Well, we need to read the lines from the trace and then perform actions on the simulator. I'll let it do that. Here we can say s dot print summary. That'd be yeah. Print summary of s. There we go. And then we'll say free sim s. And you can't do dot because it's a pointer, so you have to dereference it. And that's going to be a null pointer dereference there. So that forces us to go over here and actually return s, or ampersand s. We'll have to malloc here. I like calloc because it zeroes out the memory. So size and n. So it'd actually be 1 like this. Why does this A show up? I don't understand why that is there. It's consistently there. I have no idea what it means. Maybe it means this whole block is being appended? No, can't be. Okay. So at this point we have the size required for the cache T. The cache T is just pointers, just an array of lines. So here, we did our calc for our SimT. We also need to do a size of, this will be our line T, and the number of allocations would be the number of sets and the number of elements in the set. So the set bits, we would have to say 1 power shifted over by set bits, and we need to multiply that times lines per set. I think that's the right parameter there. And then this is going to be our S cache. It's going to equal to that. Oh, I have a one over here. All right, so make clean, make. There we go. Now run. So we have set bits 10. So number of sets is 10 to the power, or 2 to the power 10. Yep. And then the size of the cache in lines is lines per so it'd be 11 times 1024. Just verifies math. 11 times 1024. 1 1. Yep. 11264. That seems wrong. Size of cache in lines. I think the multiplication maybe is getting done first. So let's run the clang REPL. And we're going to say 1 bit shifted over by 10 times 11. Yeah, the multiplication happened first. That's the problem. So I didn't know multiplication had higher precedence than include standard IO printf out, or say puts, no, printf. We'll do %d new line semicolon. So 1 bit shift over 10 times 11 is that if we remove this, we get not that. Which is interesting is that like this is not that either. Maybe if we upcast this to be a long, oops, sorry, my bad. Why is that failing? Oh, because it needs to be like this. Like that. There we go. But still different value. Okay, well, if we pull up a browser and say see precedence, this is a learning experience for me about C precedence. I always thought that bit shifting was higher precedence than multiplication. Nope. No, that's a unit operator. But even the arithmetic operators are higher precedence than the shift operators. Okay, today I learned my intuition on that one is incorrect. So let's go ahead and say jobs vim csim.c. Go ahead and fix this down here. So it's going to be, it's a good thing I tested it. 1 bit shifted over first, like that. And then that doesn't need parentheses, but this one does. Like that. And then this one does as well. And then format specifies type int, but argument is type long. Okay. Unsigned long. Unsigned int. Oh, I'll just do long. Okay. Make. So rerun here. Okay, so now it's the proper 11,000 because 11 times 1,000. Yep. And if you multiply that times the size of, so what is the size of this thing? I'm kind of curious. Python would be that divided by this. 16. Yeah. Before we move on here, so I include all these, but I will leave one of them and I'll say size of, and we'll give it line t is equal to that, and then we'll do sub. Yeah. Okay, kill that. Okay, so it's 16 there. I'm curious if I reorder these, if it has any effect on that. I don't think it should. Yeah, it doesn't matter. Okay. Kill that. So now we're able to allocate that to the right size. When we free, we're going to have to say free s cache and also free s. Yeah. Okay. Alright. Where are we at here? Getting close to lunchtime. So I need to add these logic things. I also have to read the trace data from file, parse it, take actions on the state of simulation. So basically the meat of this problem I need to take on here, but all the other stuff is pretty much handled. All the scaffolding. I want to get some of this stuff done here. We get 5 minutes though. I don't have a lot of time. I guess the highest value thing I could do now is to just better grok what needs to happen. So reading in the lines from the trace and parsing them is like not a difficult task. Like I can do that. It's like, and then every memory operation we have to modify the simulation state. So some things that we would have to do is like up here in the simulation, there'll be like this will be a void for now. Read adder. And then adder will be some like unsigned integer, unsigned int 64t. To do. And then there'll be a, we'll say load. We'll just give it a load. Load and store. And this is going to take the SimT pointer to S. Okay. So you have our load and store. Let's look at some of these traces. Dave, I think it was one. So we have a load, store, store, store. The load okay. Let's do traces. Long. Long.trace. So store, load, store gives the actual address, all the bits. What is M again? Let's go back to the handout. It's modify. But couldn't you do a load? Alright, I'm almost done out of time here. Let's do open the cache.pdf and full screen this, and let's look at the trace. Where's the trace at? Here it is. Each line denotes one or two memory accesses. Space, operation address size. The operation field denotes I denotes instruction load. L, a data load. S, a data store. M, a data modify. Data load followed by a data store. So that's just that's a load and a store. So I could just implement that as load store. There is never a space before each I. So why did they say that we could ignore the I's? Yeah. First off, we're interested in data cache performance, so your simulator should ignore all instruction cache access lines starting with I. Okay. Okay, I think I have a better feeling now for what needs to happen. So we need to input load and store. And basically we need to see if the address is already in the cache. the data that we're interested in is already in the cache. If it is, it's served from the cache. Let's just do a stub here. See if data is in the cache already. If so, return. If not in the cache and space in the cache, put it in the cache. If not in the cache and no space in the cache, evict and put it in the cache. So we need some type of like eviction policy. I don't know if that has to be a parameter or not, but yeah. And then so that's load. And then store. We only have to perform. Okay. See if data is in the cache already. If so, return. If not in the cache, load it. It's pretty much the same operation. On eviction, so see if the cache is already, if so, record hit and return. If not in the cache, record miss. Here. If data is in the cache already, record hit and return. Else, record miss. If space in the cache, if not space in the cache, record eviction. Okay, and then store. We're going to say, okay, I need to store this data. It's in register. I'm trying to store it. We're going to see if the data is in the cache already. If it is, data's in the cache already. Then we record hit and return. Else, I think store is going to be the same thing as a load. Since data is not actually stored, store can be the same as a load. Load S, adder. Okay. All right. I'm going to take a break there then. I'll get my lunch, do some cardio, and then I'll be on in the afternoon to work more on the sim. Cool. All right. Be on later.